All right. Today we're doing office hours. We've got a test in 2 days. So today's office hours will be on Zoom. Tomorrow's will be in person, but I'm a little anxious about that. There's only 44 seats in the classroom, and we filled it out last week, and there wasn't a test last week. So I don't know how that's going to work, but we'll get it figured out. Okay, so I don't want to waste y'all's time talking about what I want to talk about. What are you guys wanting to talk about? What is the consensus of stuff that we're struggling with, stuff that we want more practice with?
Oh, um, I don't know about everybody else, but I was a little confused about some of the RS orientations, mostly because, like, I think on the practice exam, there were like a few, I think on the second to last page, there's like the big molecule that you originally like did the naming for, and then you have two, and it's like asking about the enantiomer and like diastereomer, isomer, whatever. Sorry.
No, it's all good.
And I was confused as to why, I just couldn't figure out when it like changed from an R to an S because I thought like the priority would remain the same. So like it's still kind of going in the same direction, you know? And I was kind of getting the wrong answer for that. So like I was having them like stay R, or even for that one that you have up right now. Um, like I feel like the priority wouldn't change. So why would the directionality change? Was kind of my confusion.
Okay, so that's a worthwhile question, right? So let's look at these first kind of these stereo centers and compare them, right? So they're stereo centers, they're connected to four different things. There's a methyl group, an ethyl group, and this whole group, no two groups are the same. So this is a chiral center. That counts for us. All right. So I have an unshown hydrogen. That hydrogen has to be on a dash. That's the only option, right? For all of these wedge dash structures, you see two flats, a wedge, and a dash. So this is on a dash. So our work is kind of half done for us. So we have this is group one. Here, let me talk about that more in particular, because I also think that's another sticking point for people. So I've got my chiral center. I have to assign priority based off what's attached to that chiral center. So I'm going to go one atom away. So this is a carbon, this is a carbon, this is a carbon, and this is a hydrogen. So that puts this as priority group four right off the bat. Then I have to compare what these carbons are attached to. So I have to rank these three carbons. This carbon is attached to one carbon and two hydrogens. So this is carbon and two hydrogens. This carbon is attached to one carbon and two hydrogens. This carbon is attached to one carbon and three hydrogens. So right off the bat, I know this has to be three. This carbon is attached. So then since at this point these two carbons are equivalent, I have to go one further away. Now I move one carbon further and I'm comparing these two garnet carbons to each other. This one has three hydrogens on it. This one has a chlorine, a carbon, and a hydrogen. So clearly, this side has to be my priority one, which means that has to be two. So that's how I do it. You go one atom at a time away from the chiral carbon. All right. So since my lowest priority is already on a dash, I have to figure out my RNS configuration. So I'm going to draw the shortest possible semicircle from 1 to 2 to 3. If I went this direction, I'd have to do a whole circle and a half to get 1 to 2 to 3. Or if I go this direction, It's like 2/3 of a circle. So that's clockwise. That gives me an R configuration for that chiral center. Oops. All right. I'm going to do the same thing over here. For the same reasons, my hydrogen has to be on a wedge. All right. So the way I taught you guys how to do this is I have to get this lowest priority. It's going to be the same priority groups. I have to get the lowest priority onto a dash. So that means I've got to spin a bond. So it doesn't matter which flat I anchor because neither one has my lowest priority on it. So I'm just going to anchor this guy because that side's the bigger group. So I'm going to redraw my wedges and my dashes in my flat. So I want to put my hydrogen onto the dash. That means this methyl group has to move to the flat, and this ethyl group has to move here. So now I'm going to redraw my numbers 4, 3, 2, 1. And I'm going to redraw my circle, which goes 1, 1 to 2 to 3. And that's S. Now, if you've done enough of these, you've probably noticed something. If my hydrogen is on a wedge versus on a dash with the same chiral center, it's the exact opposite configuration. This one's an R, this one's an S. So if the hydrogen's on a wedge, you can do the R and S and then just flip it. That's another way of doing it. And you'll see people teach it that way as well. Where at the start, I could have said, well, this goes 1 to 2 to 3 clockwise, but that's on a wedge. So I know it's got to be the opposite answer, which is an S. So you'll see people do that as well. But the reason that it's different is because of the orientation of the wedge and dash on the hydrogen. That's actually what we're doing. We're trying to define these chiral centers as one or the other because they look very similar, but they function differently. If you go back to what I was telling you about drug molecules, if this was a drug, one of these would work for its intended purpose and one of them wouldn't. So it's important that we know they're different molecules. Okay. So I'm going to redraw this guy. I want to figure out this other chiral center. So again, the hydrogen is already on a wedge, or sorry, already on a dash. I'm going to number this 1, 2, 3, 4. That's S. So this is R and S. And again, well, this is the same chiral center, actually. Again, the H is already on a dash. 1, 2, 3, 4. And that is S. So I'm going to write over here. We have RS versus SS. So in order for it to be an enantiomer, they have to all be opposite. Are they all opposite? No. How do I get rid of this? That's the opposite of getting rid of it. Okay, there we go. They're not opposites. If they're different but not opposites, it is a diastereomer. Does that answer your question? I know it wasn't directly on the question, but I was trying to cover some
No,
things.
no, that makes sense. Yeah, I appreciate like breaking down more the carbon, like assigning priority, because I was struggling with that a little, but that does make sense what you're doing. Thank
Yeah,
you.
the priority is a little confusing, especially since naming, we also said priority, but there it's a separate priority system for naming than it is for this is called Con-Ingold um, configuration. It's a different naming system entirely. You have to go atom by atom. And honestly, it becomes pretty intuitive. Um, like with this one, I can look at it and just tell you it's going to be 1, 2, 3 with a hydrogen as 4, just because I see that this one branches off earlier, right? Even though this carbonyl comes up, it I have to assign this one the number 2 priority before we get there. Like this carbon has a higher priority than this carbon. Done.
And it has a higher priority because it's like directly connected. Like,
Right. So we start
okay.
here.
It's because it's directly connected to two carbons, where the other one's
Right.
just one.
We start here. This is an oxygen. It gets 1. Done. This is a carbon. This is a carbon. That's a hydrogen. It gets 4. Done. Now we have to compare these two carbons. I'm going to call this the garnet one and the gold one. The garnet one is connected to 1 carbon and 2 hydrogens. The gold one is connected to 2 carbons and a hydrogen. So the gold has higher priority because of that. So I'm going to give it 2 and this 3. There's some practice problems on the active. And I think if you do those with this in mind, the pattern becomes pretty quick. Again, this one's pretty easy. 1, 2, 3. That's going to be R, right? If I make it like this, where the highest or lowest priorities on a wedge or a dash to start with, it's pretty easy, right? You don't have to do any flipping. If the hydrogen happens to be on a wedge, you could just do the opposite of that. Um, but if the trick becomes, and what I was covering today is, I don't have to do that, right? I can do a situation like this. And now the lowest priority isn't necessarily on a wedge or a dash to start with. So in this situation, the lowest priority would be this methyl group. This would be the highest because it's an oxygen.
Privilege probably in the last 2, 3 years, maybe. I mean,
No, you could tell. It had like the indoor smell.
yeah, it hadn't been, like I said.
Um, sorry. And then this is the third priority, right? This is a carbon attached to 4 hydrogens, a carbon attached to a carbon and 2 hydrogens. This is a carbon with 3 attachments to a nitrogen. That's an OH. The problem is my lowest priority is not on a wedge or a dash. So in this one, you do have to do some rotating of the molecule. So I'm
I
gonna
was,
what's up?
oh, I'm sorry. I was just wondering why the OH is higher priority than the CN, because I don't know, to me, I just was going with like atomic mass. Oh, wait, never mind. Scratch that.
Yeah,
I
so it's
just
a
realized I was picturing the table wrong.
yeah, oxygen is bigger than carbon, and that's what I compare first. Um, yeah, so this one I do have to spin this molecule. So I'm gonna lock one of these sides. So I'll lock this one because it's a flat that isn't my lowest priority, because I do have to move my lowest priority. Then what I can do is redraw my wedge dash, put my lowest priority on the wedge. So I'll keep that methyl on 4 here. That means this OH has to move, and it's going to replace the other thing. So everything that's not locked has to move. So this OH is going to go to the wedge, since that's something we haven't touched. The CN is going to go here. You're essentially just rotating everything one spot. That gets me here. Going to redraw my numbers. And we go 1, 2, 3. That's S. Counterclockwise.
But I saw this thing online where like if you switch like the places of like I guess for this one for the lowest priority with the dashed one and then the other two substituents, like if you switch those two, you would still maintain the chirality, but be able to still get your RNS.
Okay, so if the lowest priority is on a wedge, you can find the RS and just use the opposite of that.
I mean like let's say like you have your so since your methyl is your lowest priority,
Yes.
you switch that with the alcohol and then you switch the ethyl on the CN positions and you could still like rotate it and you'd still have your S, I think it was.
So you're saying do this.
Uh yeah. Well no well the OH would be where the ME would be since that'd be the lowest priority, I think. I hope this method I found one was right.
Yeah, I'm not fully following what you're saying here because I don't know how this is helpful to get to that.
Uh so since well I'd still use OH then I'd rotate, I'd still get the S.
All right. Start from here. What are you doing?
So they said that you can just switch like the OH place with the lowest priority since you want to move it to where the dashed is. And then you could do the same where you switch the CN with the ethyl.
Oh, you're saying switch this with this and this to this?
Yeah.
Yeah, I don't know if that works off the top of my head. It might work for this situation, but I don't know if that's broadly applicable.
Yeah.
That seems like an odd way to do it to me.
Yeah.
Um, it's I mean, try it. If it works for you, it works for you. I'm not gonna police your your work, but if it's not how I taught it,
I'll
I
probably
can't
just
guarantee it works. You
I'll
know?
stick to what we did in class. I was just curious to see like since whatever works if that one works or
Yeah, it's just
you
that's
know.
just one of the ones I haven't really thought about. So I'm sure that it does work. It's just um that it actually seems like it would work if you did it. I haven't tested it, so I can't endorse it.
Good.
I have a
I'm
question.
confused. Wouldn't the 1, 2, 3 be like the other way?
Oh, it would be. What am I doing?
Oh, sorry.
No, you're right. It goes 1, 2, 3. Shortest semicircle. So that yeah, that should be an R. Um yeah, I just had a brain fart, I guess. Yeah, thanks for calling me out on that. Yeah, that was wrong. This should be R. And my imaginary molecule I just made up.
I have a question.
What's up?
For the active, there was a couple questions where it was like calculate the formal charge, but we didn't necessarily, and there was like trying to give me a formula to do it.
Okay. You don't need the
Um,
formula.
that's what I thought. Can't you just look at like the amount of lone pairs and bonds and just figure it out that way?
Yeah, the amount of lone pairs and bonds is really easy. The only one that can get a little tricky is carbon. Um, which so let's say we have this carbon um versus this carbon versus this carbon. These right two carbons don't quite fill the octet rule, but believe it or not, you can have less than an octet. You just can't have more than an octet. You'll never ever have more than an octet, but you can have less than an octet. So what's happening here is this carbon kind of fits our rules of what would happen normally if we're trying to fill our octet, right? This carbon is the only one with a full octet. So it has one less bond. So it's going to have a negative charge. That's that's how I would think about it if I look at this. Like it's got an extra lone pair compared to a bond. Therefore, it's got a negative charge. Um, this one is the opposite end of the spectrum. It's missing two electrons entirely. It's only got six electrons. It's not hasn't it does not have an octet. It's a positively charged carbon. This is a neutral carbon. There's math that goes into this where you add certain numbers of bonds and electrons, but I think it's rather intuitive personally. That if you replace a bond with a lone pair, it's got a negative charge. Carbon's just kind of funny because you're never going to have more than four bonds on a carbon. So the only way you can get it is a positively charged carbon, which does exist. These exist, and we've actually saw them today. So like when I gave you a problem that looked like this zoomed in is a carbon without those lone pairs. It's a carbon with an empty octet, an empty orbital. Sorry. So that's what that carbon looks like. It's missing electrons. And we can fill those electrons by sharing a double bond with it. But then this guy we're still down electrons overall with the system. So yeah, positively charged carbons exist and they can only exist by kind of losing out on a couple of electrons. And we'll kind of see how that works as the semester goes on, like when this comes up. But it is good to know that, yeah, there's not a lone pair on this carbon. You can, in theory, have a lone pair on a carbon. This also happens in mostly organic too, but that's entirely possible.
Thank you.
Yeah, good question. I wouldn't lean too hard on the formula because, to be honest with you, it becomes intuitive within mechanisms. So usually things are starting with a charge or get a charge through arrow pushing, and you'll see that. But yes, carbons are kind of weird because we usually just assume that they're neutral, that they have four bonds or filling their octet, unless something changes. All right. So before we get off RNS, is there any other questions pertaining to kind of this topic that I can answer?
So if we do it the way where like if there's a hydrogen on a like a wedge, if we do it the way where we like do it as it is and then flip it
Yes.
and get like the right like configuration, is that okay for the test or are we
Yes, that's
expected to
fine.
like okay.
The
Okay,
only
thank
thing
you.
I'll tell you is that you cannot do that if the hydrogen is on a flat. If the hydrogen is not on a wedge or a dash, you have to rotate it. You will not get the right answer otherwise. If you guys really want to know like why this matters, is because I'll just redraw this. these two molecules, to draw it like this, like that, that's the same molecule, right? It's the exact same thing. You're just kind of looking at it from a slightly different angle. And so your clockwise or counterclockwise gets messed up. Notice we never count four as part of our rotation when we're doing our clockwise, counterclockwise. We don't really think about it. And it's because whether it's left or right of this wedge shouldn't matter to the notation, shouldn't matter to the chiral center. So we always put the lowest priority on a wedge or a dash to make sure that it doesn't matter when we do our 1, 2, 3 tracing.
Thank you.
Yes.
Hi. This might be a question like Anson had where it's like not necessarily how we reviewed it in class. But is there a way where we could find out the priorities why it's on a fissure rather than the molecule, like convert the molecule how it's looking into a fissure notation and kind of do that while it's on the fissure?
Fissure projections are often very useful for RNS. It's one of the reasons why some people don't teach Fisher at all, but when they do teach Fisher, they usually teach it as a way to determine RNS. And when you get into biochemistry, that's mostly what you're going to use Fishers for. Is that you'll have these really big molecules that have a tons of different chiral centers on them, and you have to determine whether or not it's called D or L. Whether or not a sugar is the D version or the L version based off of the chiral centers on them. Um, I'm not going to give you a Fisher projection and ask you to do RNS with it. If it helps you to do it, if you saw a video of someone doing it, um, go for it. It is a very reliable way of determining RNS.
Gotcha. I had seen it somewhere before, but I have been searching for that particular video and I can't find it anywhere. And I remember it kind of made art learning RNS a little bit easier.
Yeah, yeah.
Okay.
People do that all the time. If that's helpful for you, there's tons of resources on that. I I don't personally think about it that way, but it doesn't hurt to think about it that way.
Okay, cool. Thank you very much. Oh, and I sent in the chat and I got here a little bit late, so you might have already said it, but is this meeting going to be recorded?
It is currently being recorded.
Awesome. Thank you so much.
Yep. All right. So any more RNS questions? All right. Moving on to a new topic. I guess before we move on, are there any more questions about charges or how to calculate charges or anything like that? I do like my charge questions. Charges come up all the time in organic 1 and 2. This is a topic that will come up over and over. But yeah, I think it's a pretty easy one once you get a hold on it. The only thing that's funky is the carbons. Oxygens, nitrogens are pretty straightforward. An extra bond, a positive charge, not enough bonds, negative charge. Pretty through and through. All right, new topic. What do you guys want to talk about?
Can we like, so I was looking at the active, like for today's class. Can we go over like a question on there?
Sure. Let me see if I can get there. There we go. All right, which one do you want to talk about?
Question 8.
Question 8. Oh, wait. There we go. All right, so Yeah, this is a good one. So what's your question about it? Do you have
I just want to see how it would look like the steps of how this like each step how this would like turn to what the final product would be. So I can kind of like reverse it to figure out how it works.
okay. So the first thing I would do is kind of I guess I can't redraw everything. So redraw the main carbon containing thing. So that's what it's going to be asking about more often than not. This like OH over here doesn't have a lot of carbons on it. It's not the main part of this drawing, right?
Mm.
So, okay, let's take this arrow by arrow. This oxygen, it's using its lone pairs to do what? What is this arrow showing?
It's showing that it's going to, I guess, take the lone pairs of H. Guess take the electron from H, kind of maybe.
Okay, so where are the electrons?
Uh, they're in the bond,
What bond?
the hydrogen bond with the carbon.
Okay, not that arrow. This arrow. Arrows show the
Oh,
movement of electrons, right? Which electrons are moving?
the I guess electrons from the oxygen.
The electrons on the oxygen, right? That's where the arrow is starting. What are the electrons on the oxygen doing?
Uh, I they try and form a bond, I guess.
Yes, they're being shared with that hydrogen. They're forming a bond with that hydrogen. Yes?
Hmm.
Okay. Hydrogen can only form one bond. Yeah.
Yep.
So what's this arrow showing?
It's showing the electrons going to that, trying to get rid of that carbocation
Okay. The electrons from where?
from the hydrogen.
The hydrogen is a proton. Where are the electrons?
Yeah, I guess the carbon.
No. Where is this bond? Where is this arrow starting?
It's starting at I thought it's starting at the hydrogen. So
No. Where is it starting? Arrows show the
the
movement of
oxygen, I guess,
no. Arrows show the movement of what?
the movement of electrons.
Where are the electrons? The hydrogen is not electrons. The carbon is not electrons. Where are the electrons?
It's the bond.
That bond. Do you see that?
Yeah,
So let's be precise with our language. That bond, the electrons from that bond are going where? Are they
they're
going?
going to
Are they going
they're
to the
going to the other bond where the between the two carbons.
right? See how the arrow starts in the middle of the bond? That's showing that those the bonds from that electron. The electrons in that bond go to this bond. That's why the arrow is ending at the in the middle of a bond, not on an atom. So
Yeah.
what's going to be shown? That hydrogen gets taken by the oxygen. That's the bond that's formed there. So I'm going
Okay.
actually I'm going to remove one of those hydrogens. The
Mhm.
electrons from the bond get left here.
Okay.
So if we look at this, oops, if we look at this central carbon here between these two bonds, it has both
Mhm.
gained a double bond and lost the bond to a hydrogen. So it's a net neutral. This
Okay.
carbon on the end here has gained a double bond. So it has gained electrons. So it is now neutral.
Okay.
So that should be my answer. I can explain both of those arrows. That oxygen is forming a bond with the hydrogen. Those electrons are being left behind, are moving from that bond with the hydrogen carbon to form a double bond between the two carbons.
Yeah.
How does the hydrogen just like disappear?
It's so that's one of the reasons why I don't love this active question. Like love active in general, is I can't control this. It doesn't disappear. It actually forms water with this thing, with this OH. We'll get more into this later, but this is actually a sodium hydroxide, a base, doing what bases do, which is taking a proton,
On
forming
your exam, oh, sorry.
H2O.
On your exam, should we write the H2O too?
Yes.
Okay, cool.
I'm
So,
sorry,
yep.
back to that question. Um, since the like first arrow with the oxygen electrons going to the hydrogen, why like would you not be able to draw like to that end hydrogen on the main like chain? Would you not be able to draw a bond going from that? Or I guess, oh, I guess never mind because the hydrogen can't have two bonds. So you're just showing the main molecule
Yeah, for these
chain.
active problems, unfortunately, I can't control that. Ideally, I would want you to, I can't even draw a water on here. Ideally, the product would have a water where that O has bound to the H, and you're showing me that you know that the O has bound to an H. Um, this is a problem taken from like another unit where like they're focusing on the carbon carbon and they're not focusing on really what the they're assuming you kind of know what the mechanism is saying, but I want you to know, yes, there should be a bond between that oxygen and that hydrogen. That is what is happening, and I would like for you to show that on a test.
Oh, thank you.
Yes. So it does not disappear. It is still there. It's just sometimes people won't draw it because it's not the point of the question in the future. Because really, in the future, what we're doing is just changing the carbon skeleton. Okay. Let's see if there's another. This is a similar question. Let's see. Right. What's being shown here? What's this first arrow showing?
The electrons from the oxygen are it's going to go form a bond with the hydrogen in
It's going to
oxygen.
form a bond with the hydrogen, but that hydrogen can only form one bond. So what's this arrow showing?
It's showing the bond on that hydrogen moving to the other bond to form a double bond.
Right. So um, let me see if I can draw it. So we form a double bond here. There was a double bond here. It won't let me draw it, but what else would be in this picture?
The hydrogen that originally had that bond would now be attached to the oxygen
Right.
on that we can't draw.
Yes, it would be an H3O plus. It would be an oxygen with three bonds. So it now has the positive charge. It started neutral, it shared electrons, now it has a positive charge. There's a very clear tracing of the charge. So the OH3 has a positive charge.
Just to make sure I have this right. So the hydrogen will bond with the water molecule, and the electrons in that bond, they're gonna go to form the double bond, right?
Yeah, let me redraw it. Right, that was the original question. So what we should be getting is this. and an O. That would be the full answer to me. You're showing that there is a bond being formed between this oxygen and this hydrogen, and that these electrons, that bond between this carbon and hydrogen have broken, and those electrons went to this double bond. So we should be able to clearly trace, hey, these garnet electrons ended up being these garnet electrons. These gold electrons ended up being these gold electrons.
Does electronegativity have anything to do with where the electrons are going to go when the bond's broken?
Oh, well, yeah. So, um, yes, in a sense, having an understanding of electronegativity will start to inform kind of how this goes, right? If you notice in all of these pictures, it tends to go from more negatively charged things to more positively charged things. So either that's like neutral things using their electrons to push into positive things, or negative things using their electrons to push into neutral things. So there's always this movement from things with a lot of electrons, so that tends to be more electronegative atoms, to things without a lot of electrons, which tend to be more electropositive atoms. So there's a general theme there. In picking up on that, for the rest of class after this test, for the rest of organic 1 and organic 2, you're going to be given reactions. You're going to be given, hey, this starting material plus this starting material, how do they interact with each other and what product do you get out of it? So a lot of people who didn't get organic chemistry will tell you that there's a lot of memorization in organic chemistry. Oh, there's a lot of reactions, there's a lot of mechanisms, there's a lot of memorization. But in reality, if you can understand this pattern, that things with electrons tend to flow into things that are electron poor, then it just becomes understanding the nuances of how that happens and when that happens, and it makes the load of memorizing each reaction a lot lower. So that's a good observation. Yes, notice how this oxygen is electronegative, and that carbon, where the electrons ultimately end up, is electropositive. It's flowing that direction for a reason. That's not something you'll need to know for the test, but it's a good thing to start picking up on now. Things with a lot of electrons tend to interact with things that want electrons. Okay. Do you guys want to do a couple more of these?
Can you go over number 4 on the active?
Okay. So we have one arrow in this question, right? So what is that arrow showing? It's showing the movement of electrons, right? Always. Which electrons? What electrons are moving? Sophia.
The ones on the oxygen.
Yeah, lone pair, right? That's where the arrow starts. So what is that oxygen doing with those electrons?
Is it forming a bond?
It's using them to form a bond. It is sharing them with that positive carbon, right? It's saying, I've got a negative charge, you've got a positive charge. Let's share these electrons. So I'm going to draw this straight up like this. And this is kind of weird. I kind of hate how I'm going to put the methyl to the side, because that's kind of how you have to do it to answer this question. So that oxygen has formed a bond with this carbon, and that it's still connected to the other carbon. Nothing changed about that, right? The only thing that's changed is that oxygen is now bound to that carbon. The carbon gained electrons. So is it positive still?
No, it's neutral.
The oxygen, which was negative, has now lost electrons. Is it still
Yeah.
negative?
No.
It's also neutral, right? And then in order to get this right, we need to show that that oxygen has two lone pairs.
I'm just having a hard time drawing it out. I could have figured it out because like the way the active was.
Yeah, the way the active was, for some reason, you can't expand on this bond. So I couldn't put the O there. But as long as that oxygen is bound to that carbon, the orientation of all that doesn't matter.
Okay.
That what matters is that you know that those two that lone pair was turned into a bond between those two atoms.
Okay, thank you.
Yep. Arrows show the movement of electrons and usually the formation of bonds, but they can show breaking bonds or moving bonds. But more often than not, we're forming bonds in this class.
I have a
Yay.
question on that one.
Yeah.
How did you know that the oxygen was gonna be bonded to the what is it, hexane, instead of like the methyl group just attaching to the oxygen? Oh, is it because of the positive charge?
No, it's because of the arrow.
Okay,
So the
because
arrow shows me that these lone pair electrons are being given very, very specifically to this middle carbon here.
okay,
These arrows have to be very specific. It is saying that this carbon here is the one that is having the electrons be shared with it. So I'm forming a bond with that carbon.
okay, I see. Thank you.
Is that clear? It is the arrow that is telling me that.
Yes.
I'm not like for like the like not the full arrow ones. Are there any questions that are on here like that on off like the half arrows that you know of or nah?
No, we will not. So a half arrow is a radical. It's the movement of a single electron. We'll have a unit on radicals towards the end of this class. Very brief unit. But for the most part, we will be focusing on two electron chemistry.
I
Is what
saw
it's
like a
called.
video where your two chlorines bonded to each other, and so it wants to split it up evenly when the
Yep.
bonds break.
Mm-hmm.
Is that what
Hemolysis.
that is?
Yes. We're not there yet. But yes, that is what is happening there. Usually mediated by light. Um, uh, so like if you've ever heard of a food described as an antioxidant, that's usually something that's used to soak up radicals in the body. But we haven't talked about radicals. Well, we won't talk about radicals for a while. So you're ahead of the game, James.
Woo.
All right. Any other questions about arrow pushing? Do you guys want more examples? Do you want to, as you get later, I should have mixed these up better, but there are some questions where you have to do the opposite on active, where you have to draw the arrows. Um, so those are good practice as well. It's fairly decent actually yet. Yeah. So something like this, you'd have to look at the next picture and say, what two things have bound together, right? Well, I know that based off this picture, based off the next picture, this triple bonded carbon has to be bound to the carbonyl carbon. Have to be. It's a new bond I have to form. So this guy goes here. This double bond is broken. Where does the double bond electrons go? Well, in the next picture, this oxygen has a negative charge. So it got those electrons from that negative charge. So those have to be my arrows to explain the next picture. That's how I want you to think about it. How can these arrows explain the next picture? Lone pairs are often used to form bonds. That's the thing that I think gets people the most is they'll want to just donate a lone pair from one thing to another. They'll want to just say like, oh, this carbon's just going to give two electrons freely to this carbon or something. But no, usually when it's sharing electrons, it's forming a bond. The point is to form bonds.
This is kind of unrelated, but for the exam, is it going to be like a similar format to the practice one?
Yeah, the only thing that might be a little different is, um, these kind of questions might be a little different in terms of how I might ask you to name something or do RNS configuration. I just try to kind of make it compact here. Um, but in general, yeah, I part of the reason I wanted to give you this was so you would see like, hey, this is how I'm going to do it. I'm going to lock two positions on the Fisher projection, and I'm going to tell you exactly which carbon needs to be in which place. Um, for two reasons. One, it allows me, um, like a lot of people in these first two questions, if you're remembering, if all you've done is said, okay, every time I get things on the right, it's going to be a wedge or a dash, um, that's going to hurt you because it really depends on whether or not this front carbon gets turned into the right or the left carbon. Like it depends on how you turn the molecule. And I'm less interested that you can memorize a rule for right and left and more interested that you can see that this is a different projection of the same molecule and we're moving it around in our mind. So I gave this specifically as a way to say this is how I'm going to ask these questions. Same with same with these. Right, I'm going to tell you exactly. I'm probably going to give you the chair structures, and you're just going to have to draw on them in the way that I taught you how to do them. Um, I'm going to tell you exactly which carbon goes where, just so everything can be homogeneous. Because in reality, there's 12 different ways you could draw any one of these things, and we can't filter through those right or wrong answers. Same thing here. What I'm probably going to do for a stable Newman projection question is uh, lock lock an answer in place, which forces you to give me a very precise answer. So I'd lock a group somewhere and say draw the rest of it, just so there's only one right answer. Because like in theory, if I look at this pretty hard one, what are the biggest two groups here?
Isopropyl and phenol.
Isopropyl and phenyl. Those are the biggest groups by far. So in theory, like you want to get them anti to each other, right? So I could draw it like this, where my isopropyl and phenyl are like that, or I could draw it like this. My isopropyl and my phenyl are like this. Like I could do any number of ways. So what I'm going to do for a test is just probably give you something that looks like this. And say the hydrogen's here. Draw the most stable isomer. So you would have to know, well, if the hydrogen's there, then the bromine has to be here, and the isopropyl is going to be here. That means the phenyl is going to be here. So you'd have to fill it out based off the one thing that I've locked in place. So I didn't realize the options until I kind of saw people going through this. But yes, that's what I'm going to do for one of those as well. But yeah, this is just to keep everything homogeneous, to make sure that there's no surprises for you guys, that you understand kind of what I'm trying to tell you. And that honestly, it's for you, right? I don't want you to have to worry that these TAs are looking at a lot of tests, right? There's gonna be 300 tests, 360 tests are going through. The more consistently they can grade your work, the better off everybody's going to be. Okay. In terms of format, yeah. Okay. Another thing is, questions like this, yeah, boiling point kind of things will be on there. Functional group questions, just like what's been on 2 out of the past 3 quizzes, and on this, right? These big molecules, what functional groups are present? That's going to be on there. So, yeah, it's gonna look very similar to this.
While you're on that exam 1 review, could you go over Sawhorse and Fisher projections really quick?
Yeah. Sawhorses are very easy if you can get to Newman. Sawhorses and Newman are basically the same drawing. So I'm going to do this Newman projection. This dot is my front dot. So that's going to be this. I know that I have a group that's flat and straight down, which means that I'm going to be flat and straight down, straight up. So my Y's got to look like this. All right. So if I turn this group, so this left carbon is now this front carbon, that's going to drag this hydrogen way to the right because it's already facing me. And this OH is going to lag behind because it's already away from me. So that's going to put the OH on my left and the hydrogen on the right with the methyl straight down. That means that when I turn this, this chlorine's going to kind of go this way and the hydrogen's going to kind of go this way. So the chlorine's going to be here. Oh. Hydrogen's going to be here and the methyl's going to be straight up. So all a sawhorse is just a redrawing of the Newman slightly askew. I'm going to show you what I mean. Oh, dang it. I don't know how to do this. Can I do this? Nope. Okay. Sorry. All right, you've seen what I've done. I just have my 2 Y's from my Newman projection. I'm going to make this bigger just so it's easier to see. That's all the sawhorse is. Point blank. Done. It's literally just a copying and pasting of the Newman projection onto this line.
Thank you. That makes it a lot easier.
Yes. It is just, you're just taking something that you're looking straight at and just turning it slightly to the right or the left, however you want to think about it. All right. The Fisher. I kind of talked about this in class the other day, but what I would do is get the Fisher into a projection that you can always get it right. To me, that's getting at a wedge dash with 2 down flats. If I can get my drawing to be like this, then I can get a Fisher every time, because I imagine it's like a little dog with the ears and the tail, the bushy tail. I just need to figure out what the legs are. So I'm going to take my original wedge dash. And see if I can't convert it to this. What's nice is that this left side is already there for me. So I just now need, well, actually, that's not right. So, well, hold on. That's almost right. So now I need to convert this to a down flat. So if I'm going from an up flat to a down flat and I keep everything the same, all I have to do is switch my wedge to my dash. So my chlorine is now on a dash and my hydrogen is now on a wedge. Every time. I've just rotated 180 degrees. So I've literally flipped everything. But you'll notice a problem. Because I've locked the Fisher projection, this is my doggy head. Wow, that was bad. This is my doggy head. And this is my doggy tail. Well, right now they don't match this drawing. So I've got to rotate it to get this OH to be my tail and this chlorine to be my head. So we're going to start with the left side. I'm going to redraw the wedge dash. And I'm going to put my OH to where I want it to be. That methyl has to replace the other thing. So this methyl is going to replace that hydrogen, which means that the hydrogen only has one place to go, which is that dash. Same thing happens over here. I'm going to draw my wedge dash. I want the chlorine to be straight down. So I'm just going to put it there. That means this methyl has to replace the other thing, which is this hydrogen, which gives this hydrogen only one place to go. So now I imagine walking up to the tail of the dog while it's on its back. Are the hydrogens going to be on the left or on the right? Steven.
Are they going to be on the right?
So they're on the dog's right. Are they on? So, Steven, this hydrogen. Is it the what leg? If this is the head of the dog over here, what leg is that this hydrogen here?
That's the left leg.
The dog's left leg or your
right? I don't really know. I'm not gonna lie.
All right. So is the dash away from you or towards you?
Away.
Dash is away from you, right? If the dog's head is over here, this is its back.
So it's gonna be on the right.
It's its right leg, right? So when you walk up to it, is it going to be on your left or your right?
My left.
It's got to be on your left, which puts the methyl group on your right. Again, this hydrogen has to be on the left and the methyl group is on your right. So this is the only answer here. To me, it's helpful to get it into an orientation I can always get the Fisher into. And that requires things to be syn. You have to have this, you have to have these groups matching up. They have to be both flat in order for the Fisher to work. Um, I mean, if you get more experience, you can kind of just look at it, but that takes more experience, right? If you can look at it this angle, because you know the chlorine's got to be away from you, well, the methyl's going to be on your right. That's how I tend to think about it. But if you want to be consistent, get it into an orientation that makes sense to you before you convert it to the Fisher.
Okay.
Because I've found that for whatever reason, telling people to just imagine it from opposite the bottom and being like, oh, the methyl's got to be on my right side if I imagine it from there doesn't help too many people, even though that's how I imagine it. So if you're struggling, get it into a reliable configuration, whether that's a sawhorse or it's a wedge dash or it's whatever, and then you can get it to the Fisher.
Okay. Thank you.
I mean, the Newman's another one, right? So if let me if you can work well with Newman's, if I know the OH and the CL have to be down, I can draw it like this. I can rotate this hydrogen over here. And I'm gonna put the CL down, which rotates, keeping everything clockwise or counterclockwise to each other. Um, oh, sorry. Right. If a Newman works for you, this is just this drawing from looking at it from the top. Right. The OH is here and the methyl is on my right and the hydrogen is on my left. But you have to make sure that this front carbon is this front carbon in order to do that. So leverage the fact that you can do multiple of these and they should start building on each other, right? The goal for me here isn't necessarily that I love the sawhorse so much and you're going to see me draw it a million times. It's like the more you do these things, the more it becomes real that this is a real thing. This is I the goal is that, hey, I don't want to have to compare this to a dog in the future. I want it to be a three-dimensional object in your mind without having to make that comparison. It's one of the reasons why I wanted to use these models so bad and wanted you guys to use these models is because it cements that these are real things. These are three-dimensional real structures that exist that make up everything. You just can't see it. Well, neither can I. We can't see it. It's too small. But we know they're three-dimensional structures.
So is it that you want the two? Oh, wait, the methyl group is the bulky group. Why are we pointing Cl and OH down rather than the two methyls down?
I was just trying to get into a situation where a Fisher was easy to draw. This is by no means the most stable situation.
Okay, like because I know this is how to make it easiest to draw.
Yes.
It's how do we go from that Newman and we're like, okay, we're getting into a Fisher. How do we know that is the best position just to visualize the Fisher?
Oh, it's just it's not necessarily best.
Can there be multiple different Fishers? Like
There can be, unless I lock it.
when you say lock it in this given question,
I
what
gave
indicate
you a chlorine and an OH. So with those
oh,
already in place, the other two have to be in a certain orientation.
and the orientation is then being pointed down.
No, so what I'm saying is like by me putting this OH and this chlorine in here already, like
Mhm.
this methyl has to be on the right for this Fisher projection to be correct. So
Why does it have to be on the right?
okay, this ties in with everything else. So let's go back to this question, strangely enough. Okay. Let's simplify this. I'm gonna draw this. What is the R and S notation of these two molecules?
The are on the right, is that OH just in plain?
Yes. Sorry. Yeah.
No, you're all good. You're all good. H is on the, or am I looking at the R and S on the right or left for the specific example, or
Both.
both?
So on the left, it's 1, 2, 3. So it's gonna be S. To the right, a little trick is if the H is on a wedge, you can actually do the opposite. So this is, hold on. Sorry, I did this wrong. Oops. All right. Fixed. So if it's a wedge, it can be flipped to a dash. Okay. So the reason these are two different stereocenters. I have one R and one S. These are not the same molecule.
Why is the right an S even though it's going clockwise? Doesn't S need to go counterclockwise?
Okay, so if the hydrogen's on a wedge, if the fourth priority group is on a wedge, you can just do the rotation and then invert it.
Okay, so if I was trying to say I was on an exam and I needed to show like, hey, this is an S, I would still even write it as though it's clockwise, the arrow, like the big
Yeah, I'm not
circle
gonna I'm
arrow.
not gonna look at your work necessarily.
Oh,
You can redraw this like this. Hold on. This is also right. Right. It shows it clearer.
okay, gotcha.
But I was doing this for a reason. But yeah.
Okay,
All right. If I look down on this molecule like this and I draw both these Fisher projections, forget about the bottom, forget about this guy. The OH is away from me. For the one on the left, is the methyl going to be on my right or on my left?
it's gonna be the methyl's on a wedge in that case, so it's gonna be on the right.
Yes. For this one, is the methyl going to be on my right or my left?
The you said this one as
Sorry,
in
the right one. I forget that you guys can't see mine.
the right one, the top or bottom one.
Either one. But it has to be the OH. It has to be the one with the OH on the bottom. Where's the methyl going to be?
The methyl's still going to be on the right. No, it's a dash. So it'll be on the left, right?
Yes. So if you put the methyl on the wrong side in that above situation when you're doing your Fisher projection, it's literally a different molecule. It's the R versus the S.
So we're wanting to always put it in an R or S. Is that the case, or can it be the Fisher be on either?
No, the Fisher, in order to be the right molecule, has to be the correct stereochemistry.
and the correct stereochemistry would be, are we always supposed to get it into the R position, like flip it to be that? Like I know we can decide a molecule if it's R or an S, but when we're creating a Fisher projection, in this case we're using R because the H is on a dash in that one.
No, what I'm saying is that the Fisher projection will change depending on whether it's an R or an S.
Okay, gotcha. And because then in the case of the Newman projection you had made with the front carbon being OH, the back carbon, yeah, right there. Um, the original question was like, why is it being faced down specifically? If it was being faced up, oh, if it's being faced up too, the H's are still on the left, right?
What do you mean?
I'm just trying to figure out why is the Cl and OH facing down? I mean, because the original Newman that was there, the OH is top left, the Cl is bottom right.
Hey, Josh. Yeah, we're doing office hours. What's up?
Do you know of any other rooms besides the third floor that are open for like teaching? Like or like that are wide open areas that people can, you know what I mean?
No, I'm struggling with that myself. Yeah. What was I saying?
Is it
I
because
rotated these bonds. I rotated this bond to make it easier to draw the Fisher from. It is not something I'm requiring you to do.
yeah, exactly. I fully understand that. I'm just trying to figure out like if I had that Newman projection specifically from that specific molecule, how do I know to face that one that was made to make it easier to look at it? How do I know that I'm facing them down, which puts the H's on the left?
I put them down to mimic the Fisher because in the Fisher, the top and bottom are down. They're away from you.
Oh, oh my God, I completely understand now. It's because they're locked. It will, if it's locked, you'll always face it down with the top carbon being in the back as the back of the Newman projection, the OH being in the front because it's on the bottom.
Yeah, and I'm imagining seeing this from this angle.
Oh, okay. And you can pick whichever angle you want, right?
Yeah, I'm just trying to get you to see this as a three-dimensional object. So the
I got
challenge is to see it from different angles. The challenge is to try to imagine it in different perspectives. And the
gotcha.
challenge for me is to make sure that you guys can't memorize a bunch of rules and avoid seeing it as a three-dimensional structure and still get the right answer, which is a
Gotcha.
fun
Thank you.
challenge. Okay. Any other questions about this stuff? I'm sure there's no amount of talking about Fisher that would make Fisher easy for some people. But one of the things that's tough about Fisher is that it requires you to see it from a different perspective, to rotate bonds. Sometimes sometimes you cannot do a Fisher without rotating the bond.
Wait, sorry, this isn't about Fisher, but I just wanted to clarify what you said about the RS like notation. So like when the lowest priority group is on a wedge, you can always like just do the opposite
Yes,
wedge.
that
And
is
it's
true.
only when it's on a wedge and not when it's just like on a straight line.
When it's flat, you cannot do it.
Okay, thank
Yep.
you.
And I know that. So me putting it on a flat is a good way to ensure that you know how to rotate a molecule at least a little bit. Hint, hint.
I know you said this like a billion times, but for the RS again, like one more time, how do you number them? I'm like still a little bit like lost on that.
Okay, I'll make a really hard one to
Okay.
prioritize. Hmm. Actually, there we go. Let's do that. All right. So the first question is I'm going to start with my chiral center and I'm going to go one atom away. That's a carbon. That's a carbon. That's a carbon. That's a carbon. They're all tied so far. So, what is top left carbon bound to? Besides, yeah. So a double bond is two bonds to a carbon, and there's a hydrogen. There has to be a fourth bond. The top right carbon is bound to two carbons and a hydrogen. Right? There's an implied hydrogen here. Same with this guy. Two carbons and a hydrogen. This bottom left is bound to one carbon and two hydrogens. So if I compare the lists on all of these, which one comes out on top? Or sorry, is there a differentiator anywhere?
Bottom left.
So this has to be the lowest priority because hydrogens are smaller than carbons. The difference, the difference is that this has a hydrogen where they all have carbons. But outside of that, I cannot differentiate them. Okay, so then I'm going to move one carbon on the chain further. For this one, I have two choices. I'm going to choose the one that's most branched. And then this one, the two options are symmetrical. So now I am one, two carbons away from my starting material in all three directions. And I will compare them. Let's do these in gold. So this top left carbon, what is it bound to?
Hydrogen.
It's got two hydrogens and two carbons. So we'll do all four for these. The top right, it's bound to two carbons and two hydrogens. The bottom right is connected to one carbon and three hydrogens. Is there a difference between any of these? Bottom right, right? So this has now become my three. All right. Now I'm going to move on here. And then we've got a hydrogen. So I'm on a carbon as opposed to a hydrogen. So that's a differentiating point. So this top right is higher priority than the top left. This is harder than anything I'll give you on a test, but this is how you think about it. You go one atom at a time, make a list. What is that thing attached to? Right. So if I go down to a little bit easier of a question, this, this chiral center, well, it's bound to three carbons and a hydrogen. So the hydrogen is automatically going to be my fourth priority. The top methyl group has three hydrogens on it. The bottom left carbon it's attached to another carbon and two hydrogens. The bottom right carbon is attached to another carbon and two hydrogens. Right? So I can already tell you that this is 4 and this is 3 just based off looking kind of at those first atoms. Then I move one extra atom away. Now I'm 2 atoms away from the chiral center. The one on the left is bound to 3 hydrogens. The one on the right is bound to a chlorine, a carbon, and a hydrogen. So this has to be a lower priority than this. Let me put those, I'm going to put this 2 and 1. So that's how I'd find, this is more of a typical example. So it's about going atom by atom and making a list. What is this bound to? What is this connected to? And usually it's usually just what's branched the earliest will kind of be usually more often than not be the answer, or which one runs into a heteroatom the earliest. But yeah, I'm not trying to trick you with anything too complicated. It's a good question though. And again, there's some priority questions on the active that I think are good. I try to do the RNS active in a very thoughtful way where it starts with priority, then it asks you to do some molecule rotation, then it gets you into RNS notation. So kind of step by step, kind of hopefully builds the skills to being able to do it. All right. Any other questions?
I had a question on the functional group one. It was the very first one. I originally like the cyclohexane that's benzene, but then like now I'm confused on what's the difference between phenyl and benzene. Like, isn't it like C5 or C6H5 versus C6H6? Is that right?
Okay. So it's about a frame of reference. Let me see if I can come up with an analogy. Um, yeah, it's kind of hard to, it's like when you're I don't know. All right, whoever you cheered for in the Super Bowl, or if you didn't cheer for anybody, if we go watch Florida State play the Gators, we're the good guys to us, but we're the bad guys to them. It's about a frame of reference. Like, how are you looking at it? We're still FSU. We're still the same thing, but depending on who's the main character, which reference point you're looking at depends on what you would call us. So when benzene is part of the main chain, when it's like the focal point, it's benzene. When it's like a side chain, when it's not something you're focusing on, we'll call it phenyl. It's the equivalent of, so I don't know why they do this, but like, you know how like, all right, what is that?
Um, two, just the two carbons. What's that one called again? Ethane?
Ethane. Monkeys, methyl, eat purple bananas, methane, ethane, propane, butane. Okay. So that's ethyl. That's ethane, right? What do I call this group?
Ethyl.
Ethyl, right? There's two different names for kind of the same thing, but it depends on if it's the main thing or if it's a side thing, right? So when benzene is like the star of the show, we call it benzene. But when it's just a thing off to the side, when it's just a group, we call it phenyl. I
Okay,
don't know
so in
why
this,
we don't call it benzyl, but we call it phenyl. Benzyl
okay,
actually is a thing. It's something else. Um, well, it's a benzene ring with a carbon. I'm not going to ask you know it, but benzyl does exist, but it's the equivalent of saying ethane versus ethyl.
okay. So in question one, that's benzene.
If you called it phenyl, I wouldn't be mad at you, but
Okay,
be ready for like if it was like a multiple choice thing, it would be either,
okay,
right?
okay. That makes sense. So just so it's because in this one, like it doesn't really look like it's necessarily the star of the show because there's a lot else
I'm not going to ask
on
for you to
it.
differentiate it more than I'm going to ask for you to recognize it.
Okay,
Yep. But like if we're just like if we're shorthanding benzene away, if we're not looking at it directly, we'll just call it a phenyl. There's a phenyl ring.
okay. Thank you.
But I will not be like, well, is this main enough for you to call it a bit? No, I don't know. It will just be obvious when I call it. It's kind of like sometimes I'll call a hydrogen, sometimes I call a hydrogen a proton. It really depends on the scenario. But I just want you to not be confused if I use that terminology. That's a good question. By the way, is this a benzene ring?
No, is it? No,
No,
I don't
it's
think
not.
so.
It's most decidedly not. One thing that very often comes up that I think is really interesting is so we do all this stuff with cyclohexanes and Orgo 1. In Orgo 2, there's going to be a whole chapter about benzene rings. And these two things are very, very different, even though they look pretty similar to an untrained eye. Um, they are very different. And a lot of people will get confused on if we were doing chair structures for benzene rings or for cyclohexanes. Benzene rings flat. It cannot do a chair structure. Um, very, very different molecules, but they look similar. So that's just a heads up that it's a very common place where people get confused. They'll be like, "Oh, we did chair structures on benzenes. This is not a benzene. It's a cyclohexane." All right. Other questions?
Yeah, I'm a bit confused on boiling points and ranking boiling points.
How can I help you?
So I know generally more carbons, higher boiling point, um, properties of stronger intermolecular forces. It's like, how would I know specifically that a benzene ring, for example, less or more of a boiling point than the one directly to the next of it in the example?
Okay, so we can talk about dispersion forces, dipole dipole, which is just polarity, and we can talk about hydrogen bonding. All of these effects are going to change boiling point, are going to affect the boiling point. Um, so um, dispersion forces have to do with size and stacking. So in order for dispersion to really play a role, things have to either be things are usually going to be like a couple, like they're going to be noticeably bigger. Or like in this case, the one on the right is branched. So it doesn't pack as well, right? It's harder for it to kind of sit on top of each other versus this, where I can kind of pack it. This increases the boiling point. This makes them stick together a little bit more. So branching is a big one when it comes to dispersion forces. But one thing that I've seen people fall into is being like, well, this has an OH and this doesn't, like one carbon bigger or smaller isn't going to be a big difference in dispersion forces. But like a big chain versus a small chain is going to be a huge difference in dispersion forces. So like dispersion is probably the most important thing, but it has to be a big difference. It's only the most important because it's really easy to stack long chains of carbons. Um, it can just add up really quickly. All right. Dipole has to do with the difference in electronegativity. So for this one, I'm looking for heteroatoms. Do you remember what heteroatoms are?
Non-carbon or hydrogen atoms.
Yep. So I'm looking for OHs and NHs. So here, I've got a polar bond between this nitrogen and this carbon. This nitrogen is slightly more electronegative than these carbons. There's a dipole here. This means that if I were to look at this nitrogen, there's a partial negative at the top of this molecule and a partial positive at the bottom as that nitrogen draws electron density towards itself. Which means that if another pyridine, which is what this is called, comes by, it can kind of match up its partial negative with that partial positive. It can kind of hold itself together a little bit. That's this dipole-dipole interactions. It's two dipoles kind of sticking each other together. That's going to increase the boiling point. So if you notice, these two are intentionally made to be very similar size. Dispersion force is not relevant here. But there is a dipole here. There's also something else to consider. Hydrogen bond donors are any heteroatom with a hydrogen off of them. So nitrogens, oxygens usually. Hydrogen bond acceptor is really just anything with a lone pair. So usually that's oxygens or nitrogens. So we have a hydrogen bond acceptor here. So that plays into it as well. Here, we're just kind of ramping up the polarity a little bit. We're adding more polar bonds. There's now another set of hydrogen bond acceptors.
Which specific molecule are you talking about right now?
This pyrimidine.
So the other one is a
Yeah,
pyridine.
this is a pyridine and a pyrimidine. You don't need to know those yet.
Okay.
But yes, they are. The extra nitrogen adds more polarity. The extra lone pairs give it more hydrogen bond acceptor capabilities. And then this one's just ramped up to the max, Generally, the more heteroatoms per size, the higher the boiling point is going to be. You're just going to get more hydrogen bond donors and acceptors. Like, notice this is 1, this is 2, this is 3, this is 4. Very quickly, I can tell you that 1 and 2 are going to be 1 and 2 because there's a lot of heteroatoms for their size. This is 1, this is 2, this is 3, this is 4. It's very simply just a look how many heteroatoms are here. I mean, that's going to give me some polarity. That's going to give me some hydrogen bond donating and accepting capabilities. Like, um, let me draw this.
And to clarify, to the right of the pyridine is another molecule. That one is not a pyridine because it doesn't have uh
Talking
why
about
oh
this.
pyridine? Yes.
It is a pyridine. It's just upside down. The nitrogen's on the bottom.
Oh, okay. So why does that one have two pluses and the other one has a plus and minus?
Oh, yeah. Sorry.
No, you're good. You're good.
Because
Okay.
I make typos a lot. I'm trying to show that this negative and this positive align with each other. That's a force that holds them together. Two different versions. Because like if you have a flask of pyridine, there's been unfathomable amounts of this molecule in it. And so how hard they hold each other together can determines their physical properties.
And those are holding together very strongly.
They're holding together fairly strongly, but like something like this is going to hold together even stronger.
Okay. So it's essentially just put it upside down and see like, hey, here are the dipole moments of them. Are they going to be super strongly attracted to each other?
Yeah. How attracted to each other are they? All boiling point is a measure of the amount of energy it takes to separate molecules from each other. Like here, if I compare this to a benzene, or even to its, if I compare directly the amount of carbons, that's kind of ugly. Oops. These have the same amount of carbons. One of them solid at room temperature. Which one?
You're comparing the one you just drew on the right to which one? The benzene?
No, to the big guy here.
You're asking how many carbons?
No, I'm saying they have the same amount of carbons. Which one's solid at room temperature?
The higher boiling point means less solidity, right? Or less likely to be solid. Is
Opposite.
Are they
So
back?
if it's got a higher boiling point, it's because it's holding itself together, holding molecules together. Eventually, the stronger those intermolecular forces are, the more it's going to want to be solid at room temperature because they're solidifying, they're holding each other tight. Right? If you think about a solid, things are locked into place because their intermolecular force is so strong. A liquid, they start to kind of glide around each other. In a vapor, they're all just spread out. So which one, the left one or the right one, is going to have more intermolecular forces?
The left one.
The left one, right? The left one has all sorts of carboxylic acids, alcohols. You can see just how dense it is in heteroatoms, right? This is actually citric acid. It's what makes lemons sour. But you can isolate. So when you have sour candy, oftentimes one of the things that makes it sour is they will boil off the water from lemon stuff and isolate the citric acid, which it's a crystalline solid that you can coat on candy.
And that makes a higher likelihood of it being solid because it has a higher boiling point.
Right. It's got a higher boiling point. It's got all of these hydrogen bond donors and acceptors. It can do all of these things.
Okay. I don't know if I'm just getting too nitty gritty or this is something that we're gonna be tested on, but say you took the molecule you drew all the way on the right and you had a double bond somewhere in it. Does that change the boiling point significantly?
It would increase the boiling point. Or sorry, it would decrease the boiling point.
And why is that?
But hold on. Let me make sure I got this straight. If you added a double bond to it, it would decrease the boiling point. So it would make it more liquid at room temperature. We can actually, there's a real life comparison to this. So the reason why is because double bonds, I've been saying single bonds can rotate, single bonds can rotate, double bonds cannot rotate. There's a certain rigidity to double bonds. And we'll talk about this more later. So double bonds are rigid. So there's actually a real life thing that you've probably interacted with. So if you have these long chains of hydrocarbons, this is generally what fats look like. So like dietary fats, so butters and oils and stuff like that, right? So if I introduced a double bond into my fat, right? Well, usually it's going to look like this.
Out of curiosity, is it always have a certain amount of carbons? Like
Different fats have different numbers of carbons, and usually
Okay,
there's a
got it.
mixture, right? These things are living systems, so they're incredibly complicated.
Okay.
Okay, so the difference between this and this has to do with this double bond, right? There's a double bond. Carbon always wants 4 bonds. Yeah. So what did I have to what I had to remove bonds to what things to make these two carbons able to have a double bond?
You take away hydrogen.
I took away 2 hydrogens, right? So,
One for each, right? So 4
yes.
hydrogen on. Okay.
So I would say that this top one is saturated with carbons. Or sorry, with hydrogens. This is unsaturated.
Oh, that's what that means.
Yes. Has to do with it being not having its full amount of hydrogens. So this is a saturated fat versus an unsaturated fat. This would be a mono unsaturated fat. And we haven't talked about this yet, but it's the next chapter. If this fat is cooked for a long period of time, notice how they're on the same side here versus this where they're on a different side. So if we go back to our terminology, what is the same side? What do we call things that are on the same side?
Non-polar. I'm not sure what you're.
Is it cis?
Remember, this is trans
Termers.
and this is cis. So this would be a cis unsaturated. This would be a trans unsaturated. So if you ever heard of a trans fat, that's what that is.
Are those two, the cis and trans, diastereomers?
Diastereomers.
I don't know. I don't know how to pronounce it. I keep messing it up.
Yeah, they would be diastereomers.
Diastereomers is how you pronounce it?
Diastereomers. Yes.
Diastereomers. Thank you.
Okay. So unsaturated fats. Have you ever heard this term versus saturated?
Yes.
Which one's liquid at room temperature?
Saturated, right? Or is it the other?
It's the other. So notice saturated fats can sit on top of each other very well. They can stack very well on top of each other. That enables them to be solid at room temperature. Right? It's that dispersion force stacking.
Oh, and higher quantities of it being solid means higher boiling point.
Right. Those stronger intermolecular forces means the boiling point's going to be higher. It means the melting point's going to be higher. It means it's solid at room temperature. Unsaturated fats, because of the rigidity of this double bond, have trouble kind of stacking on top of each other. They just kind of are less stackable. So saturated fats like your oil, sorry, your butter, your lard, your coconut oil. Unsaturated fat's going to be your olive oil, your seed oils kind of deal. So it's a really good question, and it's not really that related to what we're going to do on the test, but you can see how uh, the ability for something to stack can really impact its physical properties, right? Like butter and olive oil act very differently, and it's because olive oil has one double bond in it.
Gotcha.
And
Okay, cool. That makes complete sense. Yeah.
it's a MUFA, monounsaturated fatty acid.
Cool.
Little
Thank you
dietary
very
lesson.
much.
But it plays into this, right? For the same reasons that this molecule here has a lower boiling point. It's the same reasoning, same logic. Its ability to stack on top of each other. All right. Other questions?
I just had one more question about the RS things. When you are like redrawing or flipping the molecule, um, like I'm just kind of confused on like the right way to draw it. Because I feel like the way you draw it depends on like the arrow. Like the arrow depends on the way you draw it.
Yeah.
So like, is there a way to make sure you're drawing it right?
If the lowest priority group is always a dash.
Right. But like, I mean direction wise. Like what if I draw the dash like on top and it's supposed to be on bottom? So then that like determines the way the arrow goes.
Okay. So the flats should always remain the same. Unless you purposefully flip them. Okay, so like since I have two down flats in this picture, right? Since both of these flats are going down, that means both my wedge and my dash have to be up. It doesn't matter if they're left or right of each other, but they both have to be up. You can never have a flat between the wedge and dash.
Okay.
So that's one thing that will keep you from drawing something wrong. Like you can't draw this. That will never exist.
Okay, that's what I was confused on. Okay, thank you.
Yep, this dash has to be on the same side as the wedge.
Wait, it always has to be on the same side of the wedge?
The wedge and dasher will always be on the same side from the flat.
Gotcha.
But whether or not they're right or left from each other does not matter.
Okay, cool.
Yep.
Wait, if it doesn't matter if they're on the same side from each other, then wouldn't that mess up the numbering?
That's a great question. It's exactly why we need the hydrogen either on a wedge or a dash. Because they can switch locations. When we do our R and our S, we only go from 1 to 2 to 3. We don't care where 4 is. So I actually had drawn this earlier because we had talked about it. But 1, 2, 3. See from this picture to this picture, from those two pictures, the OH and the 4 group have changed locations. They've switched, but that doesn't change my circle. So,
Gotcha.
but if the 4 was on a flat, it would matter which side it's on, and then everything gets more complicated. And so it's easier just to flip it, put it on a dash, and do your circle.
Okay, gotcha. That's why we assign priorities.
That's why you need to get the lowest priority on either a wedge or a dash. If you do not do that, then it's a 50-50 shot whether you'll get it right. There's no way to standardize it.
Okay, gotcha. Thank you.
Yep. So you guys are just super confident. You're gonna get 100. If you guys are that confident, I want to see if you can do this. Let's see. Actually, no. That's mean. I shouldn't have done that. You can try it if you want. I'll do a much easier one. Try that one. If anybody thinks they got it, show me your screen.
This is, I always get confused on this. So if it's going onto that carbon that's in between the bromine and the other carbon, is the double bond going in between the carbon carbon or in between the carbon bromine?
A double bond.
Because isn't the lone pair going to make that a double bond? One of those.
Where's a lone pair arrows going?
To a carbon.
So it's forming a single bond. You only have it's forming a bond between that oxygen and that carbon.
So if it's pointing in the middle of the line, it's going to be a bond. If it's pointing at a carbon, it's going to add a lone pair.
It depends. But in this case, a lone pair pointed to an atom means a new bond is going to form between those two things.
Oh, so it'll be three total branches. I see what, yeah, I see what you're saying.
Mm-hmm. It's usually not trying to just donate an electron. Like it's trying to form bonds or break bonds.
So in the
Sometimes
bromine,
what's
does it go, oh, sorry.
what's up?
Does it go like when it's pointed to the bromine from the line, does that make the bromine negative?
Yep.
Or like it changes bromine's charge? Okay.
And it's taking the electrons that were in that bond.
Right. So then is it just kind of like floating, like the bromine, whenever you drew it in class, it like just kind of floats?
Yep.
Okay.
Yeah, it's in a solution, so it just kind of pops right off. All right. Is that what you guys got? If it's not what you got, what happened? You need takers. People, what I found is that undergrad organic students hate forming rings. It's like the bane of your existence. You will do whatever it takes to not form a ring. You'll be like, nope, I will do the most radical stuff and start just drawing whatever because I desperately do not want to draw a ring. This bottom one's a challenge. It's really hard. But if you follow it step by step, it's not too bad. On these more complicated ones, I always start by just redrawing the starting materials. Let me make this more specific. This is just about as hard of a question as I could ask you on this. Actually, that's not true. The only way to make it harder would be to ask you to draw the arrows. So one arrow at a time. If anybody thinks they got it, I'd love to see your answer. I know y'all have cameras.
For the first one, I was still writing a bunch of notes, so I didn't see it. The bromine, what charge was it? Is it just neutral? Negative. Okay, cool.
It has gained electrons, right? It is an arrow has ended on it
Yes.
with no arrows leaving it. So therefore it has gained electrons.
Okay, cool. Thank you.
One thing that also helps with something like this is to not be afraid to draw it ugly. So even if it's not pretty, make sure everything is bound to the right thing. All right, I'll give you one more minute to work on it, and then I'll kind of walk you through my thought process.
When you walk through it,
And I just like don't really understand the part of the bottom nitrogen. Can you just explain, like, whenever you walk through it, like what exactly that's going to and like means?
All right, so it's going to this carbon.
Okay.
So hopefully that
So
can
not
be,
the whole bond, but just like that carbon.
yes, it's going to that atom, that
Okay.
carbon right there. And people love to forget that there's a carbon right before the start of a triple bond. I don't know why. It's such an, it's an, you could write a whole book on what it means to human psychology, the common mistakes you guys make.
Just to make double sure, the bromine when it goes negative or any thing when it goes negative, it's getting one extra electron, not two, right?
Right. It went from sharing these two electrons
Yeah, so it
to it
takes it
to it turning
one.
into a lone pair. So it takes one, right? In essence,
Yeah.
a bond is me sharing two electrons with you. So I kind of only have access to one. And then when I take the whole bond, I get two electrons in a lone pair.
Okay, cool. And then if I was to look at that atom and be like, hey, is there a functional group? The bromine, is that a halogen that I'd put
Yeah,
down?
it's an atom, right? It's a bromide, the negatively charged bromine. It's not really a
Okay.
functional group more than it's a thing.
And then the one on the right, that is
Oh,
an
you're saying this is an alkyl halide, alkyl bromide, right? Because it's a bromine
alkyl.
attached
Well,
to an alkyl group.
so the functional group would be alkyl halogen.
Alkyl halide, alkyl
It's
bromide. Right. Alkyl halide is just the whole all any halogen, where alkyl bromide is referring to the specific halogen.
okay. And then
Um,
the one on the right in the cyclo, well, actually not cyclohexane, I guess technically, is
yeah,
that O and ether.
yeah, that's an ether.
Cool.
You
And it's
haven't,
not cyclohexane because there's not six carbons, right?
yes, it's a cyclic ether. You haven't learned how to name that, so I wouldn't worry about
Okay.
it. So let's go step by step. This lone pair is being shared with this atom. So when a lone pair shares with an atom, we form what? Nobody? No takers?
A bond?
We form a bond. So there needs to be a bond. Oops. There needs to be, I'm going to write this down. There needs to be a bond between this nitrogen and this carbon. Period. In a story. Has to be. Okay. So then I'm going to look at, here, let me color code this. Now I'm going to look at this gold arrow. What is the gold? Where's the gold arrow starting? What electrons is it showing moving?
From the triple bond?
Right. It's using electrons from this triple bond. So these electrons will no longer be part of that triple bond. What is it using it to do?
To make a bond with nitrogen?
To make a bond with nitrogen. This arrow started where?
From the triple bond?
It started from the triple bond. So I'm going to use two of those electrons. Two of those electrons moved. Where did they go?
To the nitrogen?
Right. So they have to be lone pairs sitting on this nitrogen because I can't like form a bond with that bond, right? Like doesn't make any sense.
Yes.
So this nitrogen had a positive charge. Does it still have a positive charge?
No,
Why?
because you're moving. Is that why? Like the bond, the arrow is showing like the electrons are leaving.
Did that did this nitrogen gain or lose electrons?
No. Or is it because like there's free, like they're out of the bond? It just has lone pairs.
Did an arrow start from the nitrogen or end on the nitrogen?
And
An arrow ended on the nitrogen. Arrows show the what?
the movement of electrons.
So if I said an electron moved to a place, would you say that place has gained or lost electrons?
Gained.
Okay, so that nitrogen gained electrons. So
Yes.
it is no longer positive.
Yes. It's
And we
neutral.
can, it's neutral. We can even go back to our rules. The nitrogen now has 3 bonds, so it's happy. It's neutral. The garnet nitrogen, did it gain or lose electrons?
It lost.
It lost electrons. It was negatively charged. Now it's no longer negatively charged because it lost electrons. Now, this is where things get a little tricky. This carbon, it both gained electrons and lost electrons. So it has a net no change in its charge because there was an arrow going to it and an arrow going away from it. It both gained a bond and lost a bond. This carbon, similarly, it gained this gold bond and it lost the triple bond. So it both gained a bond and lost a bond. So its charge has not changed. And if we check this picture, what is the net charge? If we add up all the charges together in the picture on the left, what is it?
Neutral.
Neutral. If we add up
Yeah.
all the charges here.
Neutral.
Yep. We've had a conservation of both mass and charge. That's what those things mean. When you've heard people say there's a conservation of mass and charge, it's referring to this. We have the same amount of atoms, we have the same amount of electrons, and the net charge hasn't changed from start to finish. Was anybody able to get this? It's your time to brag. Ah, yeah, this is a harder one, but this is one that I expect you to be able to do in relatively short succession. I'm going to start every class from here on out, probably with a little pre-class practice problem that I'll just put up, and I'll expect to be able to do it. That looks something like this until this is the most second nature thing you've ever done. Well, I'm going to get off unless I have a really pertinent question. Is there anything that is pressing that I could answer relatively shortly that you guys have about the test, about any of this material?
One,
I just have two.
Okay.
Sorry, Sean. So I texted you, like direct message you one, but it was like, so wedges, you said something about wedges in this fissure were like on the right and dashed on the left. Is that an always definite thing or just dependent on how they're looking from like above from the dog?
What do you mean?
Like, will the wedges always be on my right and my dashes will always be on my left?
No.
Okay.
It depends on how I ask it, right? So
Okay.
this is the correct Fisher projection for this one, right? But if
Yeah.
I asked you this Fisher projection from this same,
Mm-hmm.
if I was looking at the same thing, oops. how would you fill out this Fisher projection?
You would look at it from like the other side as the start, right? From like the OH as the top.
Or the OH is the top. So where are the hydrogens?
The hydrogen is on the left in this one.
Hydrogen's actually on the right in this one.
Oh wait, why?
Because I have to look at it from this angle.
Okay.
Because the OH is on top. But if the Cl is on top, I have to look at it from this angle. So depending on which angle you're looking at it to do the Fisher projection will change whether or not your wedges are on the right or your dashes are on the right. It's one of the main reasons I've been telling you guys since the beginning that if someone tells you that, do not listen to them because they're lying to you.
Yeah. That's what they told me at ACE yesterday. I was like, so that's why I was like, okay, I'll ask. But
It works
and
if
then
I
for
was a
the
very
test,
lazy question maker and only gave you one angle the whole time, and some professors will do that. I will not do that.
oh, okay. And then for the test, like it would look something like this. Like when you say fill in the blank, it would look kind of like this right here. This is fill in the
Look
blank.
just like this.
Okay.
Yep.
Thank you.
The um yep, it's gonna look just like this.
Thanks.
My last question is for arrow pushing, do you tend to have a strategy or anything on which arrow you choose first to start, or is it just kind of you just pick one and you start and you go with the flow?
Just there's no order that changes anything. Um, if you've noticed outside of the last one I did, but like, I mean, I'm just gonna choose a random active problem. There we go. All right. So here, number 11. Notice the arrows always kind of go in one direction.
Yes.
So when we talk about it, we tend to talk about it in the direction of flow, if that makes sense. The oxygen forms a bond with a hydrogen and then leaves that bond behind to form a double bond onto the carbon. Right. So we would talk about it from oxygen to hydrogen to carbon, right? That's how I think about it. That actually is what differentiates when you would do, there's some places where you do multiple arrows or like multiple steps, each one with its own set of arrows. What differentiates one from the other? Well, usually the arrows flowing in one cohesive direction will be what I use. Like that's how I think about it, right? The bromine is you see the flow from the top right of this picture to the top left of the picture, the middle left of the picture. So the bromine is giving its electrons down to that bond, which is pushing the double bond electrons into the carbon. Right? There's a flow to all of these electrons. The oxygen is giving it down, right? It's all going kind of in one direction. So that's how I think about it. That's how people talk about it. It looks like three discrete steps, but in reality, what's happening is that this is just one big connected system, and the electrons are just kind of flowing one direction, and that's what we're showing.
Gotcha. Yeah, I guess I kind of forgot about the flow thing because I was looking at that last more hard one. It's just kind of a circle. So I'm like, oh, I wonder if he typically picks an atom first or one that's creating a bond first or something. But seeing these, it's like you can see.
Yeah, you'll
Yeah.
get the right answer either way, but so here's a secret. All of these things are reactions that you'll get to know in more detail as the semester goes on. Like you'll understand why this is happening, how it's happening, how we can control it. But in order for me to communicate that to you, you need to understand what these arrows are saying. So like um I don't know why I said that, but essentially these arrows are communicating electron flow, and that's going to be the rest. This is just if I'm honest with you, these are these are questions from chapter 16, 17, 14, like much later chapters that I've taken, because if you know electron flow, you should be able to answer these questions.
Gotcha. Thank you very much. I appreciate it, Doctor.
Yep. All right. I think that finishes it up. So thank you guys for coming. Thank you for helping me kind of get through this, and hopefully this was helpful. And I guess I'll see you guys in office hours tomorrow. I think the LAs are trying to put together a help session tomorrow evening, and there's gonna be a bunch of them, and I would highly suggest going to that. Um, I think that's gonna be very helpful. I've been very impressed with my LAs, so go get help from them. Um, try these active things, do the test review once, then erase your answers and do it again. Until you can get every single thing right. And then I think you'll be at a pretty decent position. If there's one thing you're struggling with, I would go back to the lecture notes of that thing and see if you can glean a little bit more out of it a second time through. Do those practice problems again. Go to the lecture active problems I've got posted, do those again. That's how I would study for this. Find your weaknesses based off the quizzes, based off your own self reflection, and try to address them directly. Hope that's helpful. I will see you guys Wednesday. Good luck studying. And yeah, bye.
Thank you.
All right. Thank you.
I don't actually know how to close this.